Okay, degree sequence definition. If there is a sequence of non-increasing integers a list of vertex degrees arranged in non-increasing order. Yes. A sequence is graphical if there exists some graph with that degree sequence. I think that's just better. Yeah. What are the possible degrees? So 3 vertices can why not 3? Well, we can't 0, 0, 0 works like 3 isolated vertices, comma 2, 2, 2, complete graph of 3. A vertex of degree 3 cannot exist, as we can join to at most n minus 1. Which is 2. No. Even number of odd degree vertices. Okay, I guess 2, 2. Yes. The notes prove every finite graph at least 2 vertices of equal degree. If there exists a same number of friends. I see. Alright. I should probably write that down. Not 1.17. Every finite graph has at least 2 vertices of equal degree. Okay, with n vertices, either possible degrees are 0, n minus 1. Okay, case 1. If someone has degree 0, no one can have degree n minus 1. Case 2. If no one has degree 0, comma, no one. If no one has a degree of 0, then if someone has a degree minus 1, comma, no one can have degree 0. So the possible degrees are 0, n minus 2. So the possible degrees are 1, n minus 1. The finite graph has at least 2 vertices of equal degree with n vertices, possible degree 0 to n minus 1 in case 1 is not degree 0. There's n minus 1 people. Possibilities, and also there's also, yeah, n minus 1 possibilities. So there's n vertices. So we have n vertices, but n minus 1 possibilities. Therefore, what did it say? What if all n vertices? Okay. In either case, n minus 1 possible vertex degrees and n vertices. But if all n vertices had different degrees, we would need n options. Let's see. Yeah, this kind of takes it directly from level 1.17. Cool. I don't fucking know, I'm just gonna make like random lemma 1.17. That's TikTok. What the fuck? Yes, let's look at Havlakimi. To Havlakimi, part 1, theorem. For a graphical degree sequence. Okay, let d1 dot 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 dn be a graphical degree sequence. And for any d1 plus 1 less than or equals 2, I less than or equals 2, and obviously I has to be less than or equals to n. The degree the sequence I comma d1 plus 1 d of I plus 1 di plus 1 dn is graphical. Let's do step 1, construct G and construct G prime, and then compare, compute new vertex degrees, then look at the sequence. Let's do the proofs. Okay, going backwards. Yeah, let's go backwards. Okay, construct G. Let G be a graph with vertices v1 dot 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 vn such that v of I is equals to d of I. Degree of v of I is equals to d of I. Such a graph must exist as the sequence graphical. Okay. Let G prime be a new graph with vertex set v0 union v of G and v0 v1 dot 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 v0 vi union e of G. For I has to be between what? I guess you already computed. Yeah. Okay, and then degree d of G prime of v0 equals I, and d of G prime v of j is equals to degree of graph G vj plus 1 to d of j plus 1, comma j is between 1 and less than or equals to I, and d of G prime of vj equals d of G of vj, which is equals to d of j, for j, I plus 1, right? Look at the sequence. Now our sequence has the degree. Now our sequence becomes, now the sequence of G prime becomes I, comma, v1 plus 1 plus 1 dot 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 di plus 1 dot 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 dn, which is the required sequence. Let's do the proofs instead. Here's mine for part 1. Okay. Let's do part 2. GPA graph lists the degree sequence to be 1 dot 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 dn. Suppose that d of G equals v1, v2. With d of v of I. Oh, no. That's just constructing the graph. Such that d underscore d1 plus 2 is greater than or equals to and the sequence d2 minus 1, comma d3 minus 1, dot 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 dot, d of d1 plus 1, minus 1, comma d of d1 plus 2, dot dot dot, d of n is graphical. It's just some indexing thing, I'm not going to think about it. Okay, let G be a graph. Okay. Proof graph with degree sequence. Okay, construct G, I guess. Construct G. D1 dn. Suppose that V of G equals V1 Vn with D of I equals D of I. Okay, suppose that V1 Vj is not an edge in G for 1 less than or equals to J less than or equals to D1 plus 1. Okay, we will show that in this situation we can always increase number of edges from V1 to VD. V of V1 plus 1. If V1 Vj is not an edge, then there is some I greater than V1 plus 1 such that V1 Vi is an edge because V1 is joined to D1 vertices. Since we assume D1 plus since we assumed there is a vertex U joined to Vj that is not joined to Vi, U in neighborhood of U and N of Vj minus Vi. Okay, form the graph G prime with vertices Vg and E of G union V1 Vj VIU V1 Vi VJU. When the degree sequence of G is the same as G prime has the same degree in G as in G prime, but now V1 has one more neighbor amongst V to the VD1 plus 1. So if V1 is not joined to all of these vertices, we can increase the number of them it is joined by 1 until they are joined to all of them, until it is edge swapping. Four. So we may assume neighborhood of V1 equals V2 V of D1 plus 1. Form the graph H by deleting V1 and all the edges touching it. V of H equals V of G cut V1 and E of H equals v of h. V of h cut v1, v2, v1, v2, v1, v3, v1, vd1 plus 1. Then h has the required degree sequence. Conclusion. Okay, form h. If v1 isn't connected to d1, for example, maybe v1 is connected to some low degree verse, and then you know the degrees of v2, or v3, d1, d1 plus 1. The proof says we can always draw the graphs of that. Look at this picture from the notes. Since d of vj is greater than d of v of I, can you see that swap we could do with these four vertices to fix that problem? Suppose that v1 vi is an edge. Okay. I is in d1 plus 1, I say. And j is less than or equals to d1 plus 1. Since the degree of d of vj, there's some vertex u connected to vj but not vi. Can you see this swap could do these four vertices? Okay, we can swap the edges. Okay, what's the swap? v1 vj viu. Okay. v of g union. We want v1 to connect to vj because we want it to connect to all the high degree vertices, and then u to connect to the low degree vertice vi. And we cut the original, we sever the original vju. Motivation being that we want v1 to be connected to all the high degree vertices, which is in the range of j. Yeah, that makes sense. Okay. Okay. Why does here exist the first vertex but not vi? Can you explain why? Since the proof claims that since the degree of j is greater, there must be some connected vj but not vi. Because the neighborhood there must be some vertex connected to vj, but vertex j is strictly greater than, because the degree of vj is strictly greater than vi, obviously that means it has a obviously it must have it must be connected to more vertices than vi, which is only possible if there is some vertex u. If there's some vertex u, not connected to vi. I think this is also possible if d of vj equals d of vi. Because why? Why is that actually? Suppose that vij is not an edge in G for some, and there is some I greater than v1 plus 1 v1. Okay, v1 is connected to. Okay. Because v1 vi is an edge. Because we said that v1 vi is an edge, but v1 vj is not. So neighborhood of v of j is greater than neighborhood of vi without vu. I don't know how to write. I wrote this before. I literally wrote this before. Yappers outside, man. Fuck. Neighborhood of v of j is greater than v of I minus 3 to 1. Okay, v1 is joined to d1 vertices. I said neighborhood of v of j equals neighborhood of v of I. I literally wrote this, and neighborhood of v of I and n of v of j is greater than n of v of I minus v1. So there must be a vertex u joined to Vj that is not joined to Vi. But I'm failing to make sense of it right now. I think this is correct. Okay. So neighborhood of this is equal to neighborhood of this. V1 is in Vi. Okay, but V1 is not in Vj. Neighborhood of Vi minus... Neighborhood of V of j is equals to neighborhood of V of I. Why do I compare this? Now V of j has more neighbors than V of I excluding V1. So Vj cannot be a subset of... There exists some U. Because V1 is equals... Okay. If I exclude Vi, then the neighborhood is different. Yeah, I mean, this makes sense. Weird shit. Could I say, okay, for the... For the bounds in the proof of part 2 in the notes, dd1 plus 1 minus 1 is greater than equal to dd1 is used. Could I use a different bound? Or it's the same thing, 2 less than or equals to j less than or equals to d1 plus 1. And I greater than j. Or do I have to use those bounds? I forgot. It looks so messy, but I think it's okay. Okay. The swap, so you can still find U and perform the edge swap. The key requirement is that V1 just... Okay. Do you have d1 plus 1? Okay. Okay. I'll do the proof and then move on, I guess. I'm looking at part 2. Such that dd1 plus 1. Okay, so that's what I have to write in the thing. such that degree sequence of u of j. Okay. Such that d of v of j is equals to d of v of I. This is the stronger version actually, so I'm proving it. For 2 less than or equals to j less than or equals to I plus 1, or d1 plus 1, and I greater than j. Then the sequence d2 minus 1, d3 minus 1, dot 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 d of d1, d underscore d1 plus 1 minus 1, then d underscore d1 plus 2, dot 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 dn. That's graphical. It's essentially the same proof now. Okay. Suppose that construct G or some degree sequence of G. Edge swapping. Suppose that v1 vj is not an edge. Okay, suppose that v1 vj is not an edge. That's what I suppose. And v1 vi is an edge. Then there is some I greater than j and there's some I greater than d1 plus 1 such that v1 vi is an edge as v1 is joined to d1 vertices. Alright, that's what we're saying. This thing, it's something in the low degree. Okay, now existence of u. v1 vj is not an edge and v1 vi is an edge. Since you assumed that d of v of I equals d of v of j, we know the neighborhood of vi equals the neighborhood vj and neighborhood of n of vj is strictly larger than the neighborhood of vi without vertex v1. Thus, there must be some vertex u joined to vj that is not joined to vi. That is u and nv. Okay, form the graph G prime with vertices v1 vj, viu, and v1 vi, and v1 to connect to Vj and v1, vi to connect to u, the low degree vertices. Okay, then the degree sequence of G is the same as G prime. But every vertex has the same degree of G and G prime, but now V1 is connected to one more neighbor amongst V2 to VD1 plus 1, like a higher degree vertices. VD1 plus 1. So if V1 is not joined to all D1 of them, we can increase the number of them joined by 1 until completion. Joined by 1. Yeah. Until we're done. Until we are done. Okay, now I have to form H. So we may assume the neighborhood of V1. Okay, so now we may assume neighborhood of V1 is in, or is equals to V1, V2, V of D1 plus 1, right? V1, VD1 plus 1. Okay, so we form graph H, right deleting V1 and all the edges touching it. V of H equals V of G minus cut vertex V1 and E of H equals edge set of G cut V1, V2, V1, VD1 plus 1. Then H has the required degree sequence. Three. I guess one constructs G to existence of U. 3 edge swapping, form H. That is really the heart of it. I see. And I greater than D1 plus 1. There's that, and I greater than G. Yes. Erdősködj. I'll finish this and then I'll do it. let d1 dot dn be the degree. And for every k, sum d of I less than equals to k times k minus 1. Slash sum min of k comma di. I equals 1 to n. I'm just doing this like I equals k plus 1. Then for every k, sum from this has to be less than or equals to k times k minus 1. Complete graph, whatever, count it 2 times. Yeah, the complete graph of the k counted twice plus the minimum of k comma di. Yeah, I have a shit ton of edges. I guess the motivation is that we choose some degrees up to k, examine the sum of degrees, which is k times k minus 1 for a complete graph. Correct. Or 1/2 times 2 times the number of edges, and choose 2, and then the minus 1 divided by 2. Yeah, just 2 times the number of edges, as there are k times k minus 1, 2 edges, and each edge is counted twice. Okay. Then the remaining vertices of the degree, and the remaining vertices in the degree sequence has to be can either absorb at most its own degree, or one from each of the k vertices, giving us min of k comma di. Okay. If the sum of degrees exceeds the sum, then obviously we don't have enough vertices to absorb the edges. Okay, this one I didn't really have to. I guess I just kind of knew it by heart. I think I'm pretty good with this. Let's go through the next one. Let's go to chapter 2. Holy shit, this is kind of fun. I wanted this earlier. Cool. I think this is good enough. And we should just cover more breadth now. With the proofs one time. And then ones. Now I'm done with chapter 1. Minutes. Lift some weights. Yes and no. It's greater than, then okay, because it's strictly greater than. Because degree of v of j is strictly greater than v of I, there is some vertex u that is joined to j, not connected to the I. Okay, if it's equal to, it's stronger. And because v1 is connected to v1 vertices, and there's some edge and v over here. Neighborhood of Vj is equals to the neighborhood of Vi, and neighborhood of Vj is strictly greater than the neighborhood of V1 without Vi. And Vi is not in the neighborhood of Vj is not in the neighborhood of V1. Therefore, there must be some vertex here connected to Vj that is not connected to Vi. And then, knowing that, what we can do is we can swap edges. So we can form this graph called G prime by saying E of G union. You want Vj to connect to high degree. You want to connect to high degree vertex Vj, and then you want Vi to connect to that low degree vertex U. And now we're going to cut off the original edge. So the original edge that was there, which is Vju and V1 Vi. Okay. Now, if you look at the graph G and G prime, they have the exact same degrees, right? The only thing that changes is that V1 is now connected to one more vertex among the neighborhood, among the set, v2 to v of d1 plus 1, which is the high degree of numbers you want. Okay, so if v1 is not joined to all of them, then we can just continue this process until it is. With that we can reform H. With that we know that v1, the neighborhood of v1 is equals to, or not, yeah, the neighborhood of v1 is equals to v2 v of d1 plus 1. Okay, now we can form H by deleting v1 and all of its edges. Okay, so edge set of H is equals to edge set of G. Is it G prime? No, not that much, but vertex v of G is equals to, or v of H is equals to v of G cut v1. G is G prime, but and yeah, then E of H is equals to E of G prime cut v1 v2 v of d1 plus 1. Then we have the required degree sequence d2 minus 1, d3 minus 1, v1 plus 1 minus 1. And we're done. Beautiful. Whole lot of yapping. Order shall lie, let d1 dm be a graphical degree sequence. Let be a degree sequence of a graph. Then, for every k, the sum of k from from k equals 1 to k. I equals 1 to k, d of I has to be less than or equals to k times k minus 1 plus the sum of I equals k plus 1 to n min of k comma d of I, right? Motivation being that, okay, the sum of the first k degrees must be bounded above. It's bounded above by the degree of the complete graph, which is 2 times E of G, which goes on times minus 1, plus the sum of the remaining vertices, which can absorb at most it's at most 1 from k or 1 from k or its own degree. Yeah. Let's go. Should you write this on paper? Yeah, probably. Hold on. Number of edges that contain v is d of v. Each edge contains 2 vertices, so somewhere with vertex set counts each edge twice. Yeah. Vertex that counts each edge twice. Yeah. So.
Now we can have a straight line. Yeah, I should move on. Yeah. Upload a file. Refs too. Oof. So let's do members together. For a bit of understanding. Let's move on to these sets of nodes now. My goal is to be able to memorize proof of number. Let me break it two sections. When we get there. Memorize the proofs in these nodes. And for examples, I want to understand them.
Okay, trees are one connected. They're connected but not too connected. Let's go through each one. Can you which vertex you delete? Yeah, vertices is tree left. We just for trees we just delete the vertex connected to the leaf. This will always result in a disconnected graph. Okay, for cycles, delete any vertex in its opposite path. Why isn't a cycle 3 connected runs here? Delete 2 vertices. I mean, I don't know if the correct argument is, but we can always just like take when there's 2 paths or cycles, starting with the smallest which there are always two paths to get to a vertex. So removing two vertices, one from each path, will always disconnect the graph. For complete graphs, all vertices are adjacent to each other. So we must delete every vertex. Our own, giving us a -1. Second one is kind of, I don't know, that one's kind of cookie cutter. I don't know if that's correct or not. And only vertex of the in deleting any cycle exactly has 2 minutes something. Okay, an AB separator. For non-adjacent vertices, an AB separator set of vertices as such as deleting S. Okay. For any graph G, we're adding a single vertex G and connecting by one edge to the rest of G reduces connectivity to 1. What does that mean? For any graph G regardless. What is that? Come back to this later, I guess. Some definitions. K connected if deleting every m broken K and every relative VM, deleting v1.vm results in a connected graph with a single vertex. KG, vertex connectivity. Removing is the largest number of vertices such that the graph stays connected, leading KG vertices will disconnect the graph. Same for edges, I guess. AB separator. For non-adjacent an AB separator is a set S of vertices such that deleting S leaves no paths from A to B. Minimal AB separators. Okay. Let's let pair and a separator of size K, then K of G equals to K. It's bounded above by the number of AB separators. Minimal AB separator. If a minimal AB separator has size K, then there are K independent paths from A to B. Two paths from A to B are independent only if vertex. Two paths from A to B independent if and only if they only share the start/end vertex. KF equals the minimum size in AB separator over null images. Two important facts. KFG equals minimum size of an AB separator over all non-adjacent pairs. An AB separator is saying that there is no path from A to B if a set of vertices that when you disconnect it, there's no path from A to B. So A and B are disconnected. Okay. Independent paths if they don't share endpoints are A and B. Menger's theorem state that it let A and B be okay. Menger's theorem, vertex. Let go and B be non-adjacent. If the minimal A B separator has size K, then there exist K independent paths from A to B. I'm just going to ignore the non-proofs. Maximal set of independent paths and take one vertex from each path. There will be an AB separator. This will be an AB separator. Between now and next lecture, I think why this doesn't work. We might have two independent and A and B below. My property kind of separator with the V graph might look like this. Note, our two paths are six maximal independent paths between A and B, and there's an AB separator size to prove the theorem is true, but this idea isn't going to prove it. Okay. In the non-proof, our idea is to take one vertex from each independent. Take the maximal set of AB separators and remove one vertex from each path. To disconnect the graph. However, the diagram shows that disconnecting the maximal set of there are two paths maximal independent. There's an AB separator of size 2. Not directed to. Okay, if I move this vertex and this vertex, let's see, poop, poop, shows that one vertex from disconnecting any one vertex from each path doesn't result in a disconnected graph between result in a disconnection between A and B. The vertices we remove matter. Yeah. Yeah, because you can still get to B using this path. So the vertices you choose matter. You have to choose these two. Okay. Yeah, so the maximal independent AB separator is... Okay. Okay, but a minimal size of the... Okay. Menger's theorem. If let A and B be non-adjacent vertices, let K be the minimal size of an AB separator, then there are K independent paths from A to B. Then the minimal AB separator, if you call it K, is equivalent to the vertex connectivity of a graph. Yeah. Because that's just telling you the smallest number of vertices that you have to remove to disconnect the graph, right? And that's what vertex connectivity is. It's okay, if you remove this many vertices, the graph will be disconnected. Okay, so proof. Naive idea. Take maximal set of independent paths, remove one from each path. Done. Doesn't work because which vertices you remove matter. Okay. Proof setup. Okay, let K be minimal such that a counterexample exists. Let G be a. So I'm gonna do this here. Then Menger's theorem. Setup. Okay, theorem. Let A, B be non-adjacent vertices. If K is the minimal size of, if K is the minimal AP separator, right? That's what it says? Or where the fuck is it? If K is the minimal AP separator, then there are K independent paths from A to B. Okay. There are no paths from G minus 6 from A to G minus 7. Okay, easy case. setup. One setup. Let K be minimal such that counterexample exists. Let G be a counterexample with fewest edges. Let S equals S1. Let SK be a minimal AB separator of size K. To easy case. Condition. S is not a subset of the neighborhood of A. And our sign S not subset. And that works. Capital G gamma. And sorry. And gamma B. Okay, it's not a subset of A, and S is not a subset of the neighborhood of B. And S is, what is S? S is the minimal AB separator of size K. And it's a subset of vertices that, you know, we're saying, okay, if you take all these things and remove it from G, then there are no paths from A to B. And that's size K. Okay, separator is not entirely contained in neighborhood of A or B. We replace the component containing a vertex. What's the singular A prime? What is this reduced? What can you and what can you work through this part? The separator isn't contained entirely in the neighborhood of A or B. We can form G prime by replacing the connected component G minus S with single vertex A prime. I don't know. Remember, I just like deleting this many edges. I'm just gonna keep graph, yeah. Don't have any edges in common. Show more graph theory. Okay, we can form G prime by replacing the connected component G minus S containing single vertex A prime with each vertex of S by an edge, because S is not a neighborhood of A. Are you gonna email, by the way? I don't think she'll respond. Yeah, she didn't. Maybe? Nope. I get shut. Replace the component containing A. What's this drawing? say like you have some shit like this, and it's not in the neighborhood of A or B. It's like this thing. Not sure. Not sure. Is there a diagram or example I can do to understand this? S1, S2B. This is like the AB separator, okay. X and Y, the vertices containing A. The component of G minus X containing is A, X, Y. For some reason like them. So I replace it with a single vertex A prime that is connected to each vertex in S. Now A is directly connected to S1 and S2. Okay. The component X, Y had edges among themselves, plus edges going on S. A prime has exactly S equals K edges, one to each separated vertex. Okay. Okay. We need intermediate vertices like X, Y. Okay, so we replace A with A prime. I see. Can you now explain why we can apply induction to get K-independent paths from A prime to B? So G prime is not a counterexample of this theorem, and then there are K-independent paths from A prime to B in G prime. So what the vertices are something paths from S1. And what the resulting paths from Si to B, BP of I. And then we can do the same again, since S is not in the neighborhood of B, to obtain paths from AJ to A. Measure from Sj to A. Since AJ, B are in different connected components of G minus S, they have no vertices in common. Then the paths A to B formed by concatenating each AI with BI are a set of independent paths from A to B, size K. So now we reduced the case every minimal AB separated to S neighborhood. So now note, if we have any overlap between neighborhood of A and neighborhood of B, i.e. X, every AB separator has to contain X. So deleting X from the graph uses an AB separator of size K minus 1. By induction, there are K minus 1 independent paths from A to B. There's one. Not too sure. What action applies to every key point? G prime has fewer edges than G. So Menger's theorem is true for G prime. Oh, okay. Counterexample with minimal edges. Counterexample saying that okay. Holy shit. By 12 o'clock I want to finish. By 12 I want to finish chapter 4 and then finish chapter, what is this? Chapter 5 I think, right? Which is, yeah, 4 and 5. Okay. Yeah, I'm kind of getting it. Not quite. And then actually from 12 to 1, then I'd be done. Then I'd be done with 1, 1, 3, 4, 5, 6. Right. One, 3, 4, 5, 6. Finish 2. Okay, and then we'll finish chapter 2. Should I actually say that for last, but we'll finish chapter 2 by 1. From 1 to 3, 1 to 2. The definitions and flashcards. From 1 through 6. And then from 2 through then from 2 through 3 or whatever, I guess 4, it should probably take me till 4. We'll finish chapter 7. And then from the faster I'm done, the better it is. There's only one proof I need to know. That's fine. That's really fine. At like 5 o'clock I need to, and then 4 through 8. And 4 to 5 and do chapter 8. Then from 5 to 9 to study comprension, like exams. Then 9, quickly go into office hours to ask a question with no response. Okay, 10 to 12 exam. Then from 12 through 2, I should review 12 through 2, do chapter 9. And then 2 to 4. Review all proofs. That is a beautiful plan. By 12 o'clock, finish chapter 4. Or chapter 5. And finish chapter 2 by 1. And from 1 to 2. Yeah, I think I can do this. It's fine. See my induction on S. For the chain. Lambda number R of S proof let I guess so. Expected value by linearity. And choose 3 P3. Okay, let's do the AP separator first. I don't think she's gonna make us prove the... I mean, really, I don't really want to memorize this. I really don't. It's like a fucking crazy proof. If and only if. I'm just gonna memorize this part, like theorem 2.15. Like I'm not gonna actually do anything here. Okay, where are we? Constructive proof is, this one's pretty easy. Proof on external proof. Take a minimal connected subset of edges. This certainly exists. Every finite graph, connected graph is certain. Under connected, okay. Okay, let's do chapter 4. No, chapter 4 into 5, because that makes no sense. Dude, if I had no competent exam today, oh my god, I'd be fucking smashing this. Okay, let's work. I've got paper. So I'll take it at like 5-ish. Okay, let K be minimal subset setup. Setup maker min K counterexample G counterexample with minimum number of edges. Okay, and let S okay, S be minimal. Switch that. There's a counterexample. And G be a counterexample with minimal edges. Let S be minimal such that there's a counterexample, and let G be a counterexample with minimal edges. Okay. So G is the counterexample, meaning that so G has so Menger's theorem states that for non-adjacent Menger, for non-adjacent vertices A and B, and K is the, if you let K be the minimal size of an AB separator, right? And this implies that there are K independent paths from A to B. Yeah. Okay. We're saying, okay, G doesn't have K independent paths. Let G be a counterexample with minimal edges. Not K end paths from A to B. Okay, vertex G prime, okay. G minus S, replace connected component connected to S. Replace G minus S containing A with A prime connected to each vertex of S by an edge. Okay, because S is the neighbor as the radius number edges, so G prime is not a current example. Okay, because S is not in the neighborhood of A, and the size of S is less than or equals to the neighborhood of A. Yeah, it can be at most all the vertices connected to it. G prime is less than G. So G prime is not a counterexample, meaning Mangers is true. There's k-independent paths from A to B in G prime. From A prime to B in G, sorry. Okay, let the vertices of S be sk resulting paths from Si to B. Okay, let resulting paths from Si to B be V of I. Then we can do same again. We can do the same again, since S is not in the neighborhood of gamma of B. We can make B prime. To obtain path AJ from SJ to A, to get SJ to A, AJBR in different connected components. In different CC of G minus S. They have no vertices in common. No vertices in common. So the paths A to B formed by adding each AI with BI are a set of independent paths from A to B. Of size K. Okay. So we have reduced every case. So we have reduced the case every minimal AB separator S neighborhood of A or S neighborhood of B. Okay. We're saying, okay, if it's not, some vertex is not in the neighborhood of A or vertex is not in the neighborhood of B, then we can just like boom, smash it and then put it into like one vertex and then connect to every edge in the AB separator. Every vertex in the AB separator, and they both have a size K. Okay. Note, if you have any overlap between gamma A and gamma B, then you can do the following. That's K depends from A prime to B and G. Now do the same on the other side. Go together as I path from A to B, path from A to B. Okay, come on in A and G minus N to B for that. containing B and G minus S. Connected components are disjoint. So the paths only share their endpoints A and B. No, with this case. Yes. Smash. Get that up. Double smash. Hello? Why am I... Oh, what the fuck, dude? Disgusting language. I knew something was up. Smash CC of A into A prime. Same for B. Okay, reduces edges. So Mangers applies. And they are in different, and they're in different disjoints, CCs. So change paths. Done. Step 3, remaining case. Now we assume every minimal AB separator that satisfies A subset B, A subset S, or S subset S, S subset neighborhood of A, or S subset neighborhood of B. Okay, overlap. I suppose there's some vertex X in N of A and N of B. And X is adjacent to both A and B. Every AB separator must contain X. X, B is always a path. Okay. So if we delete X from G, comma, minimal AB separator in G minus X has size K minus 1. By induction, there are K minus 1 independent paths from A to B in G minus X. Add back A, X, B, and we have K independent paths. Okay. X reduces separator size by 1 as it is a direct. Is it a direct path? That's it now? Okay. It's 1 adjacent or some shit. Overlap for A. A5. Actually, no. Neighborhood of A and neighborhood of B are disjoint. Okay, now we assume there's no overlap n of A and n of equals empty. This means A and B are at distance at least 3 apart. So A, x1, x2, xr, B, a shortest path from A to B. Since n of A and n of B are disjoint, we must have r greater than or equal to 2. At least one intermediate vertex between neighbors of A and B. Third trick, need an edge, delete x1, comma x2, and g. Let t be minimal. A, B separator. What a dense proof, bro. Holy shit. G minus x1, comma x2. Okay, claim. T equals k minus 1. Okay. Okay, so now we're doing this path. Okay, once I'm done with this though. Oh, fuck me. Edge independent paths, so you don't repeat edges. You can repeat vertices but not edges. There are paths that are from A to B that does not share any edges. They can repeat vertices though. The minimal size of AB separator is maximum number of edge paths A to B. Analogy and add vertices A prime B prime. This is what we're going to prove in G. Cavity is the maximal K such that there are K independent AB paths between any two vertices. Oh my god, bro. Holy shit. I'm gonna do this and then jump straight to chapter 7. Yeah, that's what I'm gonna do. Jump straight into chapter 7. Dude, I hate school.
How good would life would have been if I actually studied yesterday? It's 2 colors. Boop boop. We're connected. This ring is. Oh, these will give me everything. Include this. Fucking mangers, man. Yes, I can understand this is just like annoying.